PID controls stands for Proportional Integral Derivative Feedback Control and corresponds to one of the most commonly used controllers in the industry. About 90% of industrial processes are controlled using some sort of PID controllers. Its success is based on its capacity to efficiently and robustly control a variety of processes and dynamic systems, while having an extremely simple structure to implement. The PID controller consists of additive action of the proportional, the integral, and the derivative component of the error. Not all of them have to be present, therefore we also employ P controllers, PI controllers, or PD controllers. The controller only needs to compute the current error between the measured process variables and the desired set point, then calculate how much and how fast that difference has been changing over time. The controller then combines the resulting proportional, integral, and the derivative terms of the error to generate a suitable control effort for the plant. The trick is in deciding how to best combine those three terms to achieve the most efficient regulation of the process variables. The most obvious way is to use a simple weighted sum where each term is multiplied by a tuning constant or gain and the result is then added together. In this lecture, we're going to go over the basic principles of PID controllers and to expand the concept in the next lecture. By the end of this lecture, you should be able to define a PID controller, understand the influence of the controller in the temporal response, understand the practical applications of PID control, and understand the influence of the proportional, the derivative, and the integral components of the controller in the time response. PID controllers are used in most automatic process control applications in the industry. More than 90% of industrial controllers are PID controllers. This is one that can be found on Amazon for under $100. It takes the form of an amplifier that receives the desired and set point values in the form of a voltage and outputs another voltage that is proportional to the error, proportional to the derivative of the error, and proportional to the integral of the error between the set point and the current status of the system. Let's get right into it and define a PID controller mathematically. A PID controller has three components. The first one is a proportional part. We see in this control scheme we have an actuator that provides power to a process. The output of that process is measured and combined with the reference input here to generate an error signal E. The controller will use the error signal to create something that is proportional to the error. This is the proportional part. The error is multiplied by a constant Kp, and you now have the first component of the PID controller that is proportional to the error between Y and R. The second component of the PID controller is the integral component. We can now take the error and integrate the error over time and multiply that by a gain Ki, which here is a way to balance the contribution of the proportional and the integral gain in the control action. The output here now is the integral of the error times a constant. The third and final component of a PID controller is the derivative gain. The derivative gain now takes the derivative of the errors, and again we multiply that by a constant, Kd in this case, and these three constants now can be tuned to adjust the contribution of the proportional, the integral, and the derivative part in the control action. The control action is given here. It is now the sum of the proportional, the integral, and the derivative of the error. Each of these components are multiplied by a gain. So in fact, you can say that the output of the PID controller is a weighted sum of the proportional, integral, and the derivative of the error. The first branch has to do with the current error. The second branch has to do with the integral of the error, that is the error over time, the error that accumulates over time. And the third one deals with the derivative of gain, that is the current rate of change of the error. Now the relative contributions of each term can be adjusted by choosing appropriate values of Kp, Ki, and Kd so that the time response of the system follows a specified behavior. The PID controller now takes always the error and outputs a signal that is proportional to the error, that is also proportional to the integral of the error, and it is also proportional to the derivative of the error. This is the output of the PID controller in the time domain. We see the error function showing here, and you have the proportional part, the integral part, and the derivative part. Taking the Laplace transform now, we have the error of t becomes error of s, integral is 1 over s, and the derivative is simply s times e. We can now factor out e, and this is the final expression for the output of the PID controller. We'll now refer to Kp, Ki, and Kd as the proportional, integral, and the derivative gains respectively. Before we go deeper into the math, let's try to understand how a PID controller works and what is the benefit of having a PID controller as opposed to a proportional controller. Consider this example where a car is stopped at a traffic light. At this point, the desired speed of the car is 0. Let's assume that the traffic light stays red up to this point and then turns green. When the light turns green, now the desired speed that was 0 becomes non-zero. Let's assume that the desired speed is, say, 30 kilometers an hour. We can now define the desired speed of the car as this step input that goes from 0 to 30 at time t1. If you want to regulate the speed of the car from a control system's perspective, we need now a relation between the input given to the car and the output. Let's assume that this is the control scheme we are going to use to regulate the speed. So the output of the car is the speed, the input to this control system is the desired speed, and you have a controller C of S. What is the output of this controller? Most would say the output of this controller is simply the throttle angle. But think about it, do you really control the throttle angle, or do you control the speed of the throttle angle to adjust the speed of the car? If you're a good driver, you probably control the speed of the throttle angle. If you're satisfied with the speed, theta dot is 0. Let's assume that when theta is 0, you're not pressing on the gas pedal at all. When the speed of the gas pedal is 0, that means we now maintain a given speed. So the output of our controller is the speed of the throttle. Let's assume that we are driving with a proportional controller, so C equals to Kp, and the speed of the throttle becomes proportional to the error. This makes a lot of sense. When the error is 0, you are satisfied with the speed, there is no need to change the position of the gas pedal. However, hypothetically, if you are driving by controlling the position of the throttle, then an error of 0 means that the throttle needs to go to a 0 position and the car would simply stop. What is the control effort? We can define a error function, which is the desired input minus the current output, and the control effort theta dot is simply kd times the error. Initially, the speed of the car is 0 and the desired speed is also 0, and the error is 0. As soon as the light turns green, now the desired speed becomes 30 kilometers an hour. The error becomes 30 kilometers an hour. If you now take the error, multiply that by a constant kd, we have also a control effort that is very large. We're going to change the speed of the throttle, we'll press on the throttle to make the speed of the car change. As soon as that action is given to the car will now start to move and the speed will start to increase. The error now starts to decrease. If you now multiply the error by a constant, we also realize that the speed at which we change the gas pedal position changes as well and decreases. And we can continue with this process up to the point where we actually reach 30 kilometers an hour. When you reach 30 kilometers an hour, the error is 0. The control effort is also 0. We stop pressing on the throttle. So everything is right. And the car should maintain the speed. The problem is that a car has inertia. With all the velocity gained, the car will actually exceed that speed. Once the car exceeds that speed, now the error becomes negative. And as the error becomes negative, the speed of the throttle becomes negative, which means that we move the throttle back. The car now will decrease the speed and the process will continue. When the car now reaches 30 kilometers an hour and you stop moving the throttle, the car will slow down, will continue to slow down. The error will increase, press more on the throttle and keep doing small adjustments until we actually reach the desired speed. At the desired speed, the error is 0 and the throttle angle speed is also 0. How much oscillations we get? Well, in this example, we have overshoot, but if the proportional gain is small, it is likely that the system could also reach the desired speed without actually having any overshoot, but the system would be probably slower. In most of the cases, if you want a fast response, then the system may be subjected to these oscillations. And this is because the controller is only looking at the current error. It does not take into account how fast the error is changing over time. And this is the idea of a derivative gain, is to eliminate these oscillations by looking at how fast the system is behaving and anticipating future behaviors before they happen. Let's look now at the same problem, but with a proportional derivative controller. The difference here is that instead of looking at a speed control, we are looking at position control. The output of the car is now the position. We have the same control scheme, the same plan, where the output of the controller is the speed of the throttle that passes through the car transfer function. The output of the car is the speed, which means that now we need to integrate the speed to get to position. Now we are dealing with a position control problem. Let's assume that we have two traffic lights. At the first traffic light, the car is at rest and the desired position is 0. Now let's assume that at time t1, the first light turns green and the second light is red, which means now that the desired speed of the car is the second traffic light, which is in this case x0. Now let's assume that our controller is again a proportional controller, simply Kp. So Kd in this case is 0, we'll deal with this one later. So the output of our controller, data dot, is simply Kd times the error x minus y. Up to time t1, the error is 0, which means that the control effort is 0, no change in the throttle speed. At t equals to t1, the desired position becomes x0, which will result in a large error of x0 meters, and now the speed of the throttle angle will increase rapidly. As you press on the gas pedal, the position of the car starts to increase, and at the same time the error decreases. When you reach the second traffic light, the error is 0 and the speed of the throttle is 0. The problem is that now the car has gained speed and to actually pass the traffic light, the error now becomes negative, and now we have to revert the speed of the car. When the position approaches the desired position, we have the same problem again, but in the other direction. Now the car has some speed, it will go past the traffic light, the error becomes positive, and you now have to do small adjustments in the throttle up to the point where you can finally stop at x0. Again, the problem of this overshoot here occurs from the fact that the controller is only looking at the present error. It does not look ahead at how fast the error is changing. That's the idea of the derivative gain. Now let's reconsider the same example, but this time let's use a proportional derivative controller. Now the control effort becomes proportional to the error plus a term that depends on the derivative of the error times Kd, the derivative gain. We are again at a traffic light and you want to go to the next traffic light. The desired position goes from 0 to x0 at time t1. At time t1, the error is 0 and the proportional part of the controller, that is Kp times E, is also 0. The derivative of a constant is also 0, so if you now look at the second term, Kd times the derivative of E, that is also 0. At time t1, the error becomes x0, the proportional part jumps to a large value. As the car now starts to move and the position increases, the proportional error decreases. What is the derivative of the error now? We see that the error is decreasing. The derivative of a decreasing function is negative. If you now look at the derivative of the error, it's going to be less than 0. The final control effort is the combination of Kp times E plus Kd times the derivative of E. We are now taking a positive value and adding a negative value to it. We can now see that the overall control effort is lower compared to the case where only a proportional controller was used, because now we have this negative term being added to it. What is this negative term doing? The negative term indicates that the error is decreasing. The car is going towards its goal. The actual position is actually going towards the desired position, and thus, because the system is reacting the way we want, we can decrease the control effort in a anticipation of going towards a 0 error. And that's why now the overall control effort is lower. The car can slowly approach the desired position and actually stop before the second traffic light. The error slowly tends to 0 and the car can stop without any overshoot. At a steady state, the error is constant, the derivative of a constant is 0. We can immediately conclude that the derivative gain has no influence in the steady state value of the system or in the steady state error, because the derivative of a constant is always 0. With some abuse of terminology, we can say that the derivative gain in this example is added to look at the future behavior of the system by looking at how fast the error is changing and in which direction is the error changing. If the error is decreasing, the system is responding to the commands. The derivative of decreasing value is less than 0, we can now decrease the overall control effort. On the other hand, if the error is increasing, then you have to take more actions to bring the error back to 0. We now increase the control action to do that. The final element of the PID controller is the integral gain. To address the effects of the integral gain, let's consider a different example. Here we are again doing position control. So we have the desired position as the input and we have the actual position in the output. As mentioned in the beginning, the input to the car is typically the speed of the throttle, not necessarily the absolute value of the angle. For this example, let's consider that that's how we're going to control the car. The input is the actual magnitude of the throttle angle rather than its speed. There are two cars in this example. Car A is moving at a constant velocity and car B is also moving at a certain velocity. The objective is for car B to always be at the same position as car A or drive side by side with car A. The objective of the controller then is to get the position between the two cars, that is x0, to be 0 for all times. It's easy to see that if we use a simple proportional controller, we'll always have a steady state error with this control arrangement. Because now what we give to the car is the actual throttle angle, when car B reaches car A, the error becomes 0 and the throttle angle becomes 0. You're basically releasing the gas pedal when the error is 0, and car B will simply stop. So in order for car B to have a speed, there must be a steady state error. x0 must be non-zero. Again, the error is x minus y. And the control effort would be the throttle angle is equal to a proportional constant times that difference. If this difference is 0, so is the throttle angle, and car B simply stops. So this can only work provided that x minus y is different than 0. It's now easy to see that in steady state, car B will have the same speed as car A, but x0 can never be 0. So car B will always lag behind car A at a certain error, let's call that xt. This is the steady state error with a proportional controller, if this is the error in position. And this is again required for a throttle angle position to exist. You could argue that we could simply press more on the throttle. That works to some extent. We can get very close to car A, but it can never be side by side with car A. x0 can never be 0. So by pressing more on the throttle, this error decreases a little bit, but the error can never be 0. The solution to this problem is simply to use the integral component of the PID controller. Let's make now the angle be a function of the error plus a function of the integral of the error. For this same error, we know what happens to the proportional gain will simply be a constant. What happens to the integral? Well, the integral is the integral of this entire area. So the integral of the error, ki times integral of e dt, now increases over time. And as it increases over time, it is taking this area times a constant ki, it is adding that to the control effort in a way that the xt now decreases slowly. And as the error now starts to decrease, the integral component will slow down, and when you reach 0 error, the integral gain now simply becomes a constant. This is the integral part. The proportional part, as we saw before, would be a constant and now would start to decrease towards 0. When the error is 0, the proportional part is 0. But now we have an integral part that is non-zero. The integral of a 0 is simply the past value, the initial value of that integration, which is this entire area right here. The result is a controller that has a control effort different than 0 because of the integral part, even though the proportional part is 0. And that's what holds now the throttle at a given position that will allow car A and car B to go side by side. Notice that the integral controller will always have an effect on the system so long as the error is non-zero. Adding an integral controller means that the steady state error always goes to 0, because the integral component will keep integrating the error and accumulating some control effort, slowly changing the control effort up to the point where the error becomes 0, and then the integral component simply becomes constant. We didn't include the derivative gain here. Well, that's because the derivative gain would not act in steady state. In steady state, the derivative is 0, it has no effect. Of course, it has an effect on the transient part, but we covered that in the previous example. With some abusive terminology, we can now say that the integral component in the PID controller is looking at the past error of the system. To summarize, here is the implementation of the PID controller. 3 branches: the proportional, the integral, and the derivative. The proportional gain considers only the current error. The integral gain looks at the past error, takes the integral of the past error. The derivative gain anticipates the future behavior of the system by taking the derivative of the error itself. When you implement this in Simulink, the degree of the numerator is higher than the denominator. Simulink will not accept that. This is a workaround where you use a low-pass filter with a very high cutoff frequency to simulate the derivative. So when you see this in Simulink, this simply represents the derivative. Now let's look into the math in a bit more details. Let's start with the effect of the proportional integral and the derivative controller on the steady state error. For that, let's consider this simple first order system, 1 over s plus 2 controlled with a proportional controller. The closed loop transfer function is simply kp divided by s plus kp plus 2. The time constant here is simply 1 over kp plus 2. The steady state error for a step input x of s equals to 1 over s, or x of t equals to 1, can be found by calculating the difference between the desired input and the final value of the transfer function for the same step input. After some simple mathematical manipulation that we covered in lecture 7, we can see here that the steady state error can never be made 0 by tuning kp. In fact, this is equal to kp plus 2 minus kp over kp plus 2, which is simply 2 over kp plus 2. You see that the only way this can be made 0 is setting kp to -2, and this will make the system unstable. Kp needs to be a positive number, and so long as kp is a positive number, the steady state error is never 0. We can conclude that for a first order system, the proportional controller reduces the steady state error, but it can never eliminate it. I'm now going to jump to slide 14 and let's look at the effect of the integral gain in steady state error. You see the same plant, but now the controller is purely an integral controller, ki times 1 over s. We can now calculate the transfer function and apply the same theorem to find the steady state error to a step input, the desired final value minus the function final value for the same input. We see now that this tends to 0. A integral controller will always bring the steady state error to 0. Let's now go back to slide 12. We just saw that by adding an integral controller, we always have a 0 steady state error. But there is a catch. The catch is the integral component can lead to a lot of overshoot and even make the system unstable. Let's consider the same system again, but now let's look at the percent overshoot and the damping ratio. This is the same transfer function we had before. If you write this in the standard form, we see that omega n squared equals to ki, so omega n is square root of ki, and 2 zeta omega n equals to 2. Which means that zeta is simply 1 over a square root of ki. Clearly, from this expression, we see that by increasing the integral gain, the damping ratio decreases. If the damping ratio decreases, the overshoot will increase. And this is the downside of using an integral controller. If we now replace zeta in the formula for the percent overshoot, we see that this now increases as we increase the value of ki. More oscillations and higher overshoot. And this is where the derivative gain becomes interesting. Here we have a second order transfer function controlled by a proportional derivative gain. We can find the closed loop transfer function as in equation 4. We don't need to calculate anything to state that the final value of the system does not depend on kd, because the derivative of something in a steady state is 0. The derivative gain has no effect on the steady state error. If you take now this expression and look at the characteristic equation, we can find with some simple manipulation a value for zeta and another for omega n. And let's look at what we get for zeta. And the good news is that the derivative gain appears in the numerator of this equation. If we now increase the derivative gain, we are increasing the damping ratio, which means that the oscillations and the overshoot will decrease. The higher the derivative gain for the second order system, the lower the percent overshoot. If you look at the natural frequency as well and find the settling time as 4 over zeta times omega n, we'll notice that the settling time will also decrease as the derivative gain increases. We can now use the derivative gain to counteract the added overshoot by the integral gain. We can summarize this discussion as follows. For a proportional gain, by increasing a proportional gain, the overshoot increases, it has minimal impact in the settling time, and the steady state error decreases. Increasing the integral gain increases the overshoot, increases the settling time because it creates more oscillations, and brings the steady state error to 0. It always brings the steady state error to 0. Increasing the derivative gain generally decreases overshoot and settling time, and it has no impact in the steady state error, because again the derivative of a constant is 0. Let's now apply the concept of a PID controller to the speed control of a DC motor. Here is the model of a DC motor that we covered before. The input to a DC motor is the voltage applied to it, and the output could be the speed or the position. We want to develop a PID controller for a speed control. First, we need to define a desired speed. In this case, that will be omega d. Omega d has to be compared with the actual speed. This creates the error. The error is given to the controller, and the output of the controller is the voltage that is going to be applied to the motor. This entire block here is the physical structure of the DC motor, and it cannot be changed. Here is the complete block diagram. It's the same we had before, but now the PID controller is expanded into its 3 known branches. We can identify the controller and the plant. For the parameters of the DC motor, we are going to use the parameters given in the previous slide. And for the PID controller, we are going to test 3 combinations. First, a proportional controller, where Kp is 3, Kg is set to 0, and Ki is set to 0, so only the top branch is actually working. Then you're going to try the proportional integral control, where Ki is set to 15 and Kg is 0. And finally, you're going to try the PID controller, which is the same as the previous case, but now we're going to add the derivative gain. Let's see what we get in the time response of the DC motor. In this example, the desired speed is 1 radians per second. And that will occur at this point in time. We see the step input that is given to the controller. It goes from 0 to 1 at time t. The first example only deals with a proportional controller. So now the voltage applied to the motor is proportional to the error. The error can be seen here. It is simply the difference between the blue and the orange curves. We see that initially the error is 0, and when the step is given, then the error becomes 1, which is exactly this difference here. The error is then multiplied by a value of Kd. The proportional integral and derivative gains are added together, and this becomes the voltage applied to the motor. In this case, because the I and D components are 0, this is actually the same as the voltage applied to the motor. We see that the voltage is very high in the beginning because the error is large, and then the voltage is adjusted so that the speed settles at a given value. We can see that with this proportional controller there is a steady state error right here. This steady state error now results in a constant error that it gives a constant voltage applied to the motor. And this needs to occur. There must be a steady state error. If the error becomes 0, then the voltage applied to the motor would be 0. In order for a voltage to be applied to the motor, there must be a difference between the desired and the actual speed, and that's what leads to the steady state error. How we remove the steady state error? We can add the integral component. Now let's add the integral gain to eliminate the steady state error. The integral gain is 15, and the derivative gain is set to 0 in this case. Now we have again the desired input and the actual output. The difference is the error, and now we have 2 components. The first one is the error itself times Kd. This gives the blue curve. And the second one is the error times Ki times its own integral. This gives the yellow curve. We can then add the effects of P and D, and this will create the voltage applied to the motor. If you think on the proportional controller only, a steady state error must exist for a voltage to be applied to the motor. But now we have an integral gain. The integral gain will integrate that error, add that integration to the applied voltage. The applied voltage will increase sufficiently to bring the steady state error to 0. When the actual speed reaches the desired speed, the steady state error is 0. This can be seen here. With a 0 error, the proportional part of the controller becomes 0, as we can see here, and the integral gain is now integrating a 0 steady state error. But remember that it was also integrating in the past the gap between the desired and the actual output. That gap is slowly decreased, and when it reaches 0, the integral becomes constant. The integral is not 0, it's simply constant. And this is what we see here. The integral is now constant. And this is exactly what maintains that a non-zero voltage applied to the motor in a steady state, that it keeps it spinning. We can clearly see the advantage of having the integral controller. On the other hand, we also see that it created a lot of overshoot. Let's see how we can remediate that by using the derivative controller. And here we have the final PID controller. We now set the derivative gain to 0.3. You see now the overshoot is decreased by quite a lot, and now this is a more acceptable response to the system. We again have the error. The error is now multiplied by Kp, its derivative is multiplied by Kd, and its integral is multiplied by Ki. We now add all these three up, and this is what gives the voltage to the motor. Again, in steady state, we see that we have zero error, but we see that the integral part of the controller is not zero. And that is what is maintaining the non-zero voltage applied to the motor that ensures that it can spin at a constant speed. In a steady state, the derivative of a constant is zero. And you see here that in a steady state, both the proportional and the derivative gain have no effect on the behavior of the system. Let's do one more example. This is the same example we used in lecture 7. The link is in the video description. In this example, we have a simple mass spring damper system. The mass is connected to a fixed reference frame through a spring, and the mass slides on a plane. The coefficient of viscous friction between the mass and the plane is B, hence the damper. The objective is to develop a controller to control the position of the mass. We want the mass to go from its current position to a position x0. We now need to develop a closed-loop controller that will apply a force F to the mass, make the mass move, and stop exactly at x0. As a first attempt to develop a controller, we could consider a simple proportional controller. We have our reference position, which is x0, the desired position, minus the current position of the mass x, gives the error. In a proportional controller, we would multiply this by the proportional gain Kp, and now send that to the mass spring damper system, whose transfer function is simply 1 over ms squared plus bs plus k. And the output here is the position of the mass that we connect with our sum. The output of the controller is the force applied to the mass, that is F here. As we saw in lecture 7, this controller has a major drawback, and the problem here is that with a proportional controller, a force can only be applied provided that there is an error. This implies that this controller will always have a steady state error. This is easy to see. Our error here is simply defined as x0 minus x. If this is 0, which means that the mass has reached the desired position, then the force, which is simply x0 minus x times kp, is 0. When the force is 0, now the spring will pull the mass back. This problem becomes evident if we plot the error, that is x0 minus x, and the force, that is the control effort, applied to the mass. So this is F over time. Because the objective is to move the mass from its current position at 0 to x0, and then hold the mass at x0, this characterizes a step input. When time is 0, then the error is simply x0 minus x, which is 0. So the error goes from 0 to x0. This results in a large force applied to the mass because you're taking this error, multiplying this by Kp, and this gives the force. So the force will jump to a given value. Once this force is applied to the mass, now the mass will start to move. So x increases slowly, which means that the error decreases. And the force, which is simply proportional to that, will also decrease. We see that as the mass is getting closer and closer to x0, that means that the error here is tending to 0, the force is also decreasing. When the mass reaches x0, if the mass reaches x0, we have a problem because this error is 0, the force is also 0, the mass moves back. So this can only work up to a certain point, and the error will have to stabilize, the force will have to stabilize, and the mass will have to stop right before x0, not quite at x0. This is the only way we can have a force applied to the mass. So the error will decrease, the force will decrease, and when the mass gets very close to its final destination, it's going to stop. How do we solve this problem? Well, by now you guessed, we add an integral controller. So now the integral controller will look at the integral of the error. So now take the error, multiply that by Kp, and you're now also taking the error, multiplying that by Ki, and integrating it and plotting it here. So this is now the force from the proportional controller. This is now the force from the integral controller. And when you add these two up, this is the final force added or given to the mass. This implies that we need to modify the control scheme, have now the integral part, and add that to the proportional part like that. The force is now the output of that sum, which is this plus that. Very well, now that we have the integral controller, what is happening? The integral controller is looking at the integral of this error, which is the area under it. So the integral controller at the beginning will start to rise sharply because the area here is large. Of course, the area times Ki. So by controlling the integral part, you can control how fast this integral will build up. So assuming for a reasonable value of Ki, this would now start to integrate like that. So it's going to go fast at the beginning, and now the error is decreasing, the integral is getting slower. Now the integral is looking at this steady state error. So long as there is a steady state error, there is something to integrate. So it will keep going up. Even if it goes up very slowly, it will keep going up. So this adds more force to the proportional part, which will now make the mass move. And the mass will move and eventually reach x0, the error becomes 0. When the error becomes 0, what happens to the integral part? Well, it becomes constant. What happens to the proportional force? It goes to 0. The proportional force goes to 0, but now the integral force is constant. So in a steady state, the integral part holds the mass at x0, and the proportional part doesn't do anything. It did its job in the beginning to accelerate the mass, and now the integral part is holding the mass at x0. Of course, here we made an assumption that the proportional gain would start and then the integral gain would start after that. But in reality, that's not how it works. They will both work at the same time. And that's where the problem of overshoot arises. If we look at, say, a temporal response for the proportional part, such as a overdamped system like this one, reaching something close to x0, we gave this control F force to the plant. Now we have to add this two and give a lot more force to the plant, especially in the beginning. And that's where the overshoot comes from. Now if you add these two up, look at the beginning here. There is a lot more force that will make now the mass accelerate much more and overshoot x0 and then eventually settle at x0. But there is no steady state error. How to eliminate this overshoot now? Well, that's where the derivative gain comes in. We covered that in the past examples, so I'm now going to repeat it here. This demonstrates the interest of having the integral component in the loop. It will always eliminate the steady state error, regardless of the value of Ki. If Ki is very small, like a very, very small number, what happens? In the beginning, most of the force will be provided by the proportional part. And this integration, because Ki is much slower, will now take longer to build up. So the integration could be something that goes up very slowly and eventually settles at a constant value when the steady state error is 0. So what we could see is the mass moving fast towards x0 is stopping just before x0, and then the integral gain, it's still working in the background, it's slowly building up that integration error, and then we will slowly make the mass move towards x0 and settle at x0. This is exactly what we're going to see in the video that will follow. We'll apply this to a linear cart, and you'll see that the mass will initially jump and then it slowly moves towards its destination. And that is because the integral gain is too low, and we set too low on purpose so that you can see the effect of this integration building up and eliminating the steady state error slowly. In this series of experiments, we are going to apply a PID controller to control the position of this cart. The cart has a DC motor that rotates and makes the cart slide along that linear rail. The motor is powered by this power amplifier here, which is controlled using the microcontroller. The PID controller is implemented in this Arduino microcontroller. The controller is designed to make the cart move to this desired position and stay at that desired position regardless of external disturbances applied to it. The current position of the cart is measured using a potentiometer that is connected to the motor. The potentiometer measures the actual position of the cart and sends that to the microcontroller. The input to the microcontroller is the desired position of the cart, that is 30 centimeters in this example. First, we are going to try that with a proportional controller only, then with a proportional and the integral controller, and then finally with a PID controller. Two things can be observed. The first one is when the card is let go from rest and reaches that position, and the second one is when a disturbance is applied. In this case, the disturbance is simply a manual displacement that is applied to the cart. The Arduino code used in the lab to implement this controller is available on Canvas.
Yeah, pure proportional control. Try to get to 30 centimeters. So you can see that it does an okay job getting there. There is still a small steady-state error there. You can see that there's oscillations. And burning those disturbances doesn't help with steady-state error. Control control. Try to get to 30 centimeters. You can see here the integral control kicks in and tries to get it to exactly that position. You get a disturbance. So this is PID control. You can see that the derivative now helps mitigate the overshoot. The integral control still kicks in trying to get it to zero state error. Okay, so this is the instability demo. Let's try and keep the same position, so we have a small disturbance. It's going to try and compensate because it shows unstable gains. It's going to exponentially increase until it eventually crashes. Example of instability.